So hello and namaste everyone and welcome to lecture 9. Okay, so let me make sure I can see the list of participants so that I know who is raising hands if there is a need. All right. Okay. So in the last couple of lectures, if you have noticed, we have started computing the Betti numbers, right? So we have started computing the Betti numbers of a given simplicial complex, right? So this is what we have started doing. So as a first example, we looked at this very basic simplicial complex and we computed its homology in different coefficients and used the homology space to compute the corresponding Betti number, right? So we did that both in the usual homology framework as well as the reduced homology framework. Okay, and last time we sort of said, okay, let's look at one complicated example. So this was the example we considered and we asked, can we say something about the homology of this simplicial complex and maybe even the Betti numbers of this simplicial complex. Okay, so as I said last time, okay, so this simplicial complex has one non-trivial hole, at least visually that's how it looks like. So one would hope that if we did this calculations formally, we would be able to see that Betti 1 for this simplicial complex turns out to be 1 as well. Okay, so that is what we wanted to verify and we started doing those computations and today we will just continue them. Okay, so there is one change that I have made in this example corresponding to what we had last time. So last time I had sort of labeled the vertices as 0, 1, 2, 3. Okay, I realized that the 0 vertex is going to confuse us with the 0 chain, right? So hence I have sort of relabeled the vertices as 1, 2, 3, 4. Okay, so please keep this in mind. All right. Okay. So our goal now is to look at the Betti numbers of this simplicial complex. Okay. So last time we somehow said that Betti p for p bigger than equal to 2 and p less than equal to -1. Okay, both in the usual and reduced homology case, one can show that it is 0. Okay, so maybe I didn't cover all the cases, but the way we did in this simple example, if you sort of repeat that procedure, you'll be able to see that for all p bigger than equal to 2 and p less than equal to -1, indeed this simplicial complex has 0 Betti number. All right. Okay, so now our focus is to compute Betti 0 and Betti 1 for the above complex, right? So in particular, I would want everyone to pay attention, right? How the quotient operation ensures that we sort of ignore this filled cycle over here. Okay, so that is what I want everyone to focus on, right? So let's try to compute Betti 1. So in order to compute Betti 1, the idea is that we have to first look at this H1 space, right? So this H1 space is what is of interest to us, and in order to compute H1, we have to look at these three vector spaces and the corresponding linear maps between them. So we need to look at C2, we need to look at C1 and C0, right? So this is what we need to look at. Okay, so let me just draw this picture again. So this is 1, 2, 3, 4, and this triangle is filled, right? So let's look at what C2 is, right? So C2 is a vector space which is made up of the two chains. So since we have this one triangle, right, observe that C2 has the 0, 2 chain and the other chain, which is this 1, 2, 3, right? So this is the um, two chains that would be there in C2. Okay, and one can see that C2 is a vector space, right? And now let's look at C1. So C1 consists of all possible sums of one chains, right? So in this simplicial complex, you can see that there are 5 edges, right? So you take these 5 edges and form all possible combinations. So you start with the 0, 1 chain. So this is no combination of any of these edges, right? So then you take one edge, that is 1, 2. So this will be one chain. This is another one chain, and so on. You go all the way up till 3, 4. So these one chains have support exactly 1, meaning notice that this has 5 edges, right? So the support can go all the way from 0 to 5. So by support, I mean all those faces before which the coefficient is 1, right? So here there is just one phase before which the coefficient is 1. In other words, you can think of this 1 2 as 1 times 1 2 plus 0 1 3 plus, maybe I'll use a different color so that it's clear that I'm referring to the coefficients and so on. So this will be 1 3 1 4 and 2 3 and 3 4, right? So you can think of this as 1 1 2 0 1 3 0 1 4 0 2 3 and 0 3 4, right? So you can see that the support of this one chain is 1 because there is only one phase for which the coefficient is non-zero, right? So that's why the support of this one chain is 1. So you can see that we have 5 such one chains, right, whose support is 1. Then we look at the one chains which have support 2, right? So this is 1 2 plus 1 3 and so on all the way up till 2 3 plus 3 4. Then we look at one chains whose support is 3. So you can see we have 1 2 plus 1 3 plus 1 4 and so on, and we could keep going. And the final one chain we write is the one where the support is over all the 5. I mean the support is all the 5 edges. So there is a typo here. This should be 1 2 plus 1 3 plus 1 4 plus 2 3 plus 3 4. All right. Okay, so this is what your C1 vector space is, right? And can one of you volunteer and tell me what should be the dimension of this vector space? What should be the dimension of this vector space of C1 vector space? What do you think its dimension should be? Yes, Agnit, go ahead.
5.
Please justify.
Because there are 5 edges and they will form the basis.
Sure, the basis consists of 5 elements, which is 1 2 1 3 all the way up till 3 4. So this is just one choice of a basis. You can equivalently come with several other options. So this is like the standard basis that one can think of, right? So that's the reason C1 has dimension 5. And in the same way, we can now look at what C0 is in the context of this. So notice that there are 4 vertices, right? So this is the zero chain with support 0, right? Or I mean the support is doesn't include any of these 4 vertices. Then you look at the 0 chains where the support is 1. Then you look at the 0 chains where the support is 2 and so on. And the final 0 chain is the one where the support is 4. Right. So in this way you can construct C2, C1, C0, and I'm sure most of you must have guessed that the dimension of C0 is 4. Right. So this has dimension 1, this has dimension 5, and this has dimension 4. Right. So we have all the information now, and we can now proceed towards computing Betty 1, right? So so recall what Betty 1 is. So Betty 1 is dimension of H1, and what is H1? H1 is Z1 quotient with B1, right? So first let's compute what B1 is, right? So what is B1? Well, B1 is the image of DABA2, right? So we now need to compute the image of DABA2. So what I'll do is I'll take DABA2 and apply it on all the elements that are present in C2, right? So I take DABA2, I first apply it on 0. I hope you agree that the output of this would be 0, right? And then I apply it on 1 2 3. So the output of this will be 1 2 plus 1 3 plus 2 3. That's it, right? So this is the information that we have, and from this we can see that B1 would be made up of these 2 elements. Is this okay? Can one of you volunteer and tell me what is the dimension of B1? What is the dimension of B1? And please accordingly tell me what is the basis as well. Okay. What is the dimension of B1? Would one of you like to volunteer? Yes, Ganesh, go ahead.
It should be 1.
It should be 1. Please justify.
The basis vector would be 1 2 plus 2 3 plus 1 3.
Very good. Is this okay? So this is a one chain, right? And that can be thought of as that can be used to generate any element over here. Very good. Okay, so the dimension of B1 is 1. So now let's look at what Z1 is, right? So Z1, recall, is the kernel of DABA 1, right? So this is what we have to do. So we have to go over here, right? And basically identify all possible one chains which will be mapped to 0. Okay, so that is what we are required to do. So we will sort of go over it in a sort of what should I say, in a sequential fashion as stated over here. So what we will do is we will first look at the DABA1 applied on 0. So clearly this is 0. So we can include this, we can include this over here, right? So you can see that Z1 has 0, right? So now let's look at the different one chains which have support 1, right? So if I apply DABA1, let's say on 1, 2, right? So the output of this will be 1 plus 2. So clearly this is not 0. Hence 1, 2 will not be there in Z1. Right, so in the same way you can see that 1 2 1 3 blah 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 all the way up till 3 4, none of them would be present in Z1 because none of them would be mapped to 0 under DABA1. Right, so next let's look at the one chains which have support 2. Right, so let's look at 1 2 plus 1 3. Right, so if you take 1 2 plus 1 3, so DABA1 of 1 2 plus 1 3, so this will be DABA1 of 1 2 plus DABA1 of 1 3. So I'm using the linearity property of DABA1, and now DABA1 of 1 2 is 1 plus 2 and DABA1 of 1 3 is 1 plus 3. So these ones cancel off and I end up with 2 plus 3. Right, so again this is not 0. Right, and in the same way you can see that if you apply DABA1 on any of these one chains whose support is 2, okay, none of them would be taken to 0. Right, so you can verify this yourself. Right, so now we come on to the one chains which have support 3, right, and one can see that indeed there are two one chains with support 3, okay, which are taken to 0. Right, so first let's verify it algebraically. Right, so DABA1 of 1 2 plus 2 3 plus 1 3, so one can see that this will be 1 plus 2 plus 2 plus 3 plus 1 plus 3. So you can see that everything cancels off and indeed we get this 0. Right, and in the same way you can verify that this second one chain which has support 3, this again will be taken to 0. Right, so these are the two one chains with support 3 which indeed will be taken to 0 under the DABA1 operator. Hence these two one chains have been included in Z1. Now let's go back to the figure. Right, so let's go back to the figure and see what these two one chains represent. So the first one chain that was there in Z1 was 1 2 plus 2 3 plus 1 3. So you can see that this one chain corresponds to this one cycle over here. Is this okay? So this one chain corresponds to this one cycle over here, and the other one chain that was there in the kernel was this one 1 3 plus 3 4 plus 1 4. Right, so this, as you can see, corresponds to this part over here. Right, and in the same way you should be able to guess that this one chain, right, which has support 4, right, so which is basically 1 2 1 2 plus 2 3 plus 3 4 plus 1 4. Right, so if you apply DABA1 on this, I hope you agree that this also will be taken to 0. Right, so in this way you can sort of go over it one by one, right, and check which of the one chains are taken to 0, and from this one can conclude that indeed Z1 has these many elements. Is this okay? All right, so can one of you tell me what is the dimension of Z1? What is the dimension of Z1? Please volunteer. What is the dimension of Z1? Yes, Ichit, please go ahead.
It's 2.
2. And what is the basis for this?
Sir, 1 2 plus 2 3 plus. Okay.
So this is one thing, and the other is 1 plus 1 4.
3.
So we have to make sure that these two vectors or these two elements in this Z1, they are linearly independent as well as they span. Right. So the spanning part is easy to see because if you take this and if you add this to this, right, this and this will cancel off and you will end up with 1 2 plus 2 3 plus 3 4 plus 1 4, right? So the spanning part is easy to see. One has to also separately make sure that these two elements are linearly independent. For that you have to see if there is a linear combination of this one chain and this one chain, and is there a possibility that there is a non-linear, non-trivial linear combination that equals 0, right? So the different linear combinations that are possible is 0 times this plus 1 times this, right? Or alternatively it is 1 times this and 0 times this, right? And alternatively the last is 1 times this and 1 times this, right? So these are the four possible three possible linear combinations that you can consider, and you can explicitly see that in neither of these three cases, okay, would the end result be 0, right? So that's the reason these two vectors are linearly independent, right? And hence the dimension of z1 is 2. Very good, right? So now we have with us what B1 is and what Z1 is, and I think we should now be in a position to compute H1. So recall what H1 is. H1 is taking the quotient of Z1 with respect to B1, right? So I'm explicitly doing this example so all of you can see what exactly does this quotient operation do, right? And how it ensures that we count the right number of things. Right, so to begin with, observe that dimension of Z1 is 2. So if you directly looked at the dimension of 2 and somehow interpreted that as the number of holes in the simplicial complex, I hope you agree that we would end up with a wrong answer, because just looking at Z1 will tell us that the answer would be 2, but intuitively we know that the answer is 1. Right, so let's see how taking the quotient of Z1 with B1 ensures that the answer ends up being 1. Right, so recall what do we do when we quotient Z1 with respect to B1. The idea is that we sort of say that some elements are equivalent. In particular, our idea is that we set all the elements of B1 as 0, right? So B1 has some 0, but when we do the quotient operation, what we are saying is that every element in B1 we will think of as 0. So what does this statement formally mean? Formally, it has to be interpreted from the perspective of this equivalence relation. So remember what we said. We said that when we do this quotient operation, it is equivalent to saying we come up with an equivalence relation. And what is that equivalence relation? We will say that two elements x and y in Z1 are equivalent if their difference lies in B1. Right? This is how we define the equivalence relation. So let's see if the two elements in B1 are equivalent or not. So the question is 0 equivalent to this other one chain that is there in B1, right? So in order to verify whether this is equivalent to this, what we have to ask is we take this 1 2 plus 2 3 plus 1 3, subtract from it 0, and we ask whether this lies in B1 or not. But that is trivially true, and hence it follows that this two elements, we will think of them as being one and the same, right? So from this it follows that the equivalence class of 0 will include 0 and this other one chain, right? So in this way you can see that we are now thinking of both these elements as the new 0, right? That's the way to interpret it. And of course, the equivalence class of 0 includes these two elements, and in the same way the equivalence class of this other element, that also includes these two elements, right? So the equivalence class of 0 is equal to the equivalence class of any other element in the equivalence class of 0, right? So this relationship actually holds true. So this is the summary so far. Whenever we take the quotient with B1 operation, what we are saying is that we are now going to declare some elements as 0. Right, that's what this quotienting operation means. Because we have now declared some elements to be 0, okay, a few other elements in Z1 will now become similar. Okay, so what I mean by that, see in Z1 you have these two elements. So these two elements are now to be interpreted as 0. Now what about these two elements, right? So earlier Z1 included 4 elements. Now what we are asking is, these two elements we are thinking of them as 0, but what about these two elements? Are they separate or are they to be interpreted as one and the same? So more formally what we are asking is, are these two elements equivalent to each other or not, right? So in order to verify whether these two elements are equivalent or not, what we need to do is we take the right hand side, subtract from it the left hand side, right? So I would like to say over here, right, in Z2 subtraction is equivalent to addition, right? Because 1 minus 1, okay, this is so maybe I'll write it at some other place. Okay, so 1 minus 1, okay, this is equivalent to 1 plus minus 1. However, in Z2 addition, the inverse of 1 is itself, right? So this is equivalent to 1 plus 1, right? So in the same way, y minus x in when we do the Z2 related operations, this can also be interpreted as y plus x, right? So this is something you need to keep in mind, because in Z2, every element is its own inverse, right? So accordingly, one can see that in any of these vector spaces, that is Z2, C2, or in general ZP, CP, BP, and so on and so forth, every chain is its own inverse, right? So whether we write y minus x or y plus x, it doesn't matter. All right. Okay, so now the question that we would like to ask is whether these two elements are they equivalent or not. In order to verify that, we take the addition of these two entries and see if the result actually lies in B1 or not, right? So if you take the addition of what is there on the right, so it is 1 2 plus 2 3 plus 3 4. So I think yeah, sorry about this. So I think there is some mistake somewhere. So let me make sure what is the chain on the right. So it should be, so this should be 1 4 here. So this is a mistake. All right. So this, I think this now makes sense. All right. So let's look at this. So we have this one chain on the right. So we take this one chain, and to that we add this one chain on the left. So let's do that. Okay. So we take 1 2 plus 2 3 plus 3 4 plus 1 4, and to that we add this other thing 1 3 plus 3 4 plus 1 4. So I hope you agree that these things cancel off, and we end up with 1 2 plus 2 3 plus 1 3, right? So if you sort of go back a bit, you would be able to see that this entry over here, okay, indeed lies in B1, and that's why one can conclude that indeed these two entries are equivalent. All right. Okay, so consequently, one can say that the equivalence class of this entry actually includes these two elements now, right? And similarly, as I said before, the equivalence class of this one chain and the equivalence class of this one chain, okay, they are one and the same, right? So in H1, we end up with only two elements. One is the equivalence class of 0, and the other is the equivalence class of this entry, right? So note that in Z1, we had 4 elements, right? However, we somehow set some equivalence between the different elements of Z1, and we now end up with only 2 elements in H1. So the first element is the equivalence class of 0, and the second element is the equivalence class of this, right? And now if I ask you what is the dimension of this vector space, okay, you can see that this alone is a basis for this vector space, and from this one can conclude that Betty 1 is 1, right? So if we sort of go back to this diagram that I had above, right, let's see what is happening. So in this diagram, what we started off was, this is one cycle, this is another one cycle, and this is another one cycle. So we had like 3 non-trivial one cycles, right? However, what we then said was, this one cycle I will think of as 0, right? The boundary of this filled triangle I will think of as 0, right? That's what this quotienting with B1 implies. Thereafter, what happened was, this one chain and this one chain are now equivalent, right? So what I'm saying is 1 2 1 3 plus 1 4 plus 3 4. This one chain is equivalent to 1 2 plus 2 3 plus 3 4 plus 1 4. Right, so you can see that this one chain and this whole one chain, right? Maybe I'll draw it slowly. So this one chain, okay, this is the first one chain, and the one chain that is there, surrounding the whole, this figure, right? Those two one chains are now equivalent. Okay, so at the end of the day, we only end up with one trivial one chain, which is basically the equivalence class corresponding to this one chain, right? And that is what we are counting. So I hope you are able to see how this quotienting operation ensures that we don't overcount, and it also ensures that we don't undercount, and hence one can see that Betty 1 is 1, and this is exactly what we had expected. Okay, so let me pause here for a couple of seconds. If you have any questions, this may be the best time to ask them. Yes, Agnit, go ahead.
Sir, I think there's just a typo here. Can you scroll a little up?
Yes.
Uh, yeah. So yeah, in the second line, I think it will be an equal to. Right?
Here you mean?
No, no. In the up in the second line of the page.
Second line of the page.
Uh, okay. Wait. Yeah.
Here?
Uh, yes, yes, yes.
So you are saying that this relationship is not true. Is that what you're saying?
Uh,
This relationship is true because you can cancel this 1, 2 and this 2, 3, and you can see that you will end up with what is there on the left. So this relationship is true.
okay.
So,
Okay.
right. So I just
Okay. Fine.
proved
Fine.
it.
Yeah.
Right. So I just proved it in a different way. So let's think of this as x and y. Right. So our goal was to check if x is equivalent to y, and that requires us to show that y minus x lies in B1. Right, this is what our goal was, and what I did was I took this y over here and added some element from B1. Right, so this element is an entry in B1, so I took an element in B1, added to this y, and I showed that look, indeed there is an element in B1 such that if you add it to this y you get x. That's the way I wanted to show it over here. Is
Okay.
this
Okay. Yeah.
okay?
I got it. I got it. Okay.
All right. Are there any more questions? By the way, the lecture notes are uploaded on the file in the file section. Okay. Last time I couldn't do that. I apologize for the same. But for this class, I have managed to upload it in the file section. So in case there is something that is bothering you and you would like to stare at it for some time, and I am scrolling the screen, it may be a good time to. It may be a good idea to look at it in parallel. All right. So are there any more questions? Please feel free to ask them. So if you don't understand these things, the lectures henceforth are going to be, based on this, and hence, you'll find it difficult to understand those lectures as well. Okay, so I encourage you to ask me any questions at this time, and it's also important that you study things in parallel. Otherwise, you will be left behind. Okay, so please read regularly. I hope you are noticing that in the lecture notes, I point out which part of the textbook you have to look at and so on and so forth. So that is the minimal thing you have to do. However, in case there is something that you don't understand, you should go ahead, explore things on your own, and study things accordingly. All right, so I don't see any more raised hands, so maybe we can advance. Okay, so in this way we saw that beta 1 turns out to be 1, right? So I hope you are able to see that the way we do this quotient operation ensures that we don't overcount, as at the same time it also ensures that we don't undercount, right? So now as I said at the beginning, okay, we wanted to compute both Betty 1 and Betty 0, and now we have finished computing Betty 1. So now we will focus on computing this Betty 0. Right, so let's do that. So for Betty 0, we have to look at these three, these three vector spaces C1, C0 and C minus 1. So we will first look at the usual homology framework. By that I mean we will set this C minus 1 to be the trivial vector space. So when we set it to be the trivial vector space, it has just one element which we will interpret as the additive identity. That's all. Okay, so we are so the symbol over here is to be interpreted as the additive identity, right? You could have as well written this to be some symbol plus, or some whatever symbol you like, maybe some of our letters from our Indic languages, right? You could have written something like this and you could have interpreted that as well as the additive identity. Okay, so nothing would have changed. We sort of give this the label 0 or the symbol 0 just so that it's clear in one shot what it means. All right, so this is C1, this is C0, and C minus 1 is the trivial vector space. So now we have to ask what is C1 and what is C0. So these things we already listed in the as part of our previous computation, so I'm not going to do that. So C1 is the collection of all possible 1 chains and C0 is the collection of all possible 0 chains. right? So so we have to now focus on computing H0. So H0 is Z0 quotiented with B0. Okay, so that's what we are interested in doing. So what is Z0? Z0 is the kernel of DABA 0, right? So because we have set this C minus 1 to be 0, right, every element in C0 will be mapped to 0, right? That's how this operator is defined. So notice what we have. We have C0, we have a bunch of elements here, and C minus 1 only has 0, right? And this is how the DABA 0 operator is defined. So every element in C0 will be mapped to 0, and because of this reason, Z0, which is the kernel of DABA 0, will be the whole of C0. Okay, so that is the first part. Now what remains to compute is the the image of DABA 1. Okay, so we need to be now careful. Let's see how we compute the image of DABA 1, right? So in order to do DABA 1, we have to first recall what C1 is, right? So C1 has 0, it has these 5. So let me maybe draw this simplicial complex also here. So this is 1 2 3 4, and this is the triangle that is filled, right? So the different edges are 1 2 1 3 1 4 2 3 3 4. So these are the different one chains with support 1, and then you have 1 2 plus 1 3 blah 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 all the way up till what is it 2 3 plus 3 4 and so on, and finally you have 1 2 plus 2 3 or maybe I'll write it in the right order. So 1 2 plus 1 3 plus 1 4 plus 2 3 plus 3 4, right? So these are the different possible what should I say one chains, right? And we have to basically look at all possible 0 chains that these one chains get mapped to under DABA 1, right? So that is the question that we have to answer, because recall that B0 is the image of DABA 1, right? So let's see what happens to 0. So 0 gets mapped to 0, right? So that's why we include 0 over here. Now let's see where 1 2 gets mapped to, right? So 1 2 gets mapped to 1 plus 2, right? So accordingly you can see that we have included this 1 plus 2 in the image of DABA 1, right? And accordingly you will see that this part will get mapped to 1 plus 3, this will get mapped to 1 plus 4 and so on, right? So accordingly you see that we have 1 plus 2 1 plus 3 1 plus 4 2 plus 3 and 3 plus 4. So these 0 chains correspond to the boundary of the 5 edges that we have. So notice that in this simplicial complex we have 5 edges. So if you take any of these 5 edges, like the one chain corresponding to that, and you apply DABA 1 to it, you will notice that you will end up with one of these 5 0 1 chains. Okay, now I am claiming that in the image of DABA 1 there is 2 plus 4 as well, right? There is 2 plus 4 as well. So this is a 0 chain, right? This is special in the sense that notice that in this simplicial complex we don't have an edge 2 4. We don't have an edge 2 4. That's why there is no one chain for which one chain that gets mapped to 2 plus 4. Nevertheless, I am saying that this 2 plus 4 is an element in image of DABA 1, and the reason is that there is another what should I say one chain which is mapped to 2 plus 4 under DABA 1, and what is that one chain? It is 2 3 plus 3 4, right? So if you apply DABA 1 on this, you will end up with 2 plus 3 plus 3 plus 4, and these cancels off and you end up with 2 plus 4. So this 2 plus 4 is what I have written over here, right? And you can sort of look at these different one chains with support 2, and you can see that whatever you do, you end up with one of these 6 possibilities, right? So you can sort of verify it in a brute force fashion and see that you end up with something like this. And then there is one more thing that we end up with. So let's say we look at the one chain 1 2 plus 3 4, and you apply DABA 1 on this, right? So this will give you 1 plus 2 plus 3 plus 4. Right, so you can see that this 0 chain that I have included in V0, this will be the output of this one chain, that is 1 2 plus 3 4, right? And if you see if you take any other one chain, right, that will give you only one of these, what should I say, 1 2 3 4 5 6 7 8 possibilities. Okay, so whatever one chain you take, it will only give you one of these 8 possibilities, right? So that's why B0 will indeed be this vector space that is specified over here, right? So let us stare at what we have over here and let us see if it has anything interesting. So notice that it doesn't include everything from C0, right? So C0 also has the let's say the zero chain 1, right? So the zero chain 1 is the zero chain corresponding to the vertex with label 1, right? So it has this. So you can see that in B0 there is no such zero chain. In particular, there is no such zero chain whose support is 1, right? And similarly, there is no zero chain whose support is 3, right? So all those things are not present in B0, right? So that is something we have to observe, right? And now one can immediately ask, okay, what is the dimension of this B0, right? So the dimension of B0 is 3, and the reason for this is that these 3 elements that are there in this B0, they can be viewed as a basis for B0, right? Like for example, let's see if it spans, right? So definitely 1 plus 2 can be used to create this, 1 plus 3 can be used to create this, and 1 plus 4 can be used to create this. Can one of you tell me how to create 2 plus 3? We are checking whether this spans this space, right? So I would like one of you to volunteer and tell me how can we create 2 plus 3 using these basis elements. Can one of you volunteer? Yes, Durjati, please go ahead.
First two element 1 plus 2
Right, very
plus
good. So 1 plus 2 plus 1 plus 3. So this can be viewed as 1 plus 2, right? Plus 1 times 1 plus 3, right? So this will give you this 2 plus 3. So in this way, you can see that we can create this element, and similarly, you can see that you can create this element. So the only thing that now remains is how to verify if we can create this element as well. So can one of you volunteer and tell me how to create 1 plus 2 plus 3 plus 4? I saw Mehul had raised his hand. Mehul, would you like to volunteer and tell me how to create 1 plus 2 plus 3 plus 4?
Yes, sir. So 1 times 1 plus 2
Mhm.
plus 1 times 1 plus 3 and plus 1 times 1 plus 4. Since 1 is 3 times, so 2 will get cancelled out and 1
Very
will
good.
remain.
Very good. Very good. So exactly. Okay. So this is how one can see that this sum will actually give 1 plus 2 plus 3 plus 4. Right. So in this way, we can see that indeed this spans this space, and one has to verify that this also is linearly independent. I will, presume that all of you now are, competent enough to do those verifications, right? So I will leave it sort of as an exercise for you all. So one can indeed see that this forms a basis for B0, and since the basis has 3 elements, one can conclude that the dimension of B0 is 3, right? Now let's go back to this Z0. So Z0 is C0, right? So C0, recall, is the collection of all possible 0 chains. And since there are 4 vertices over here, you can think of the 0 chains corresponding to these 4 vertices, right? Those as the basis for C0, right? And one can conclude that the dimension of C0 is 4. And from there, since Z0 and C0 are one and the same, one can conclude that the dimension of Z0 is 4. Right? So notice what I am doing now. Okay, so I want you to pay careful attention to the way I compute beta 0. Right? So what is beta 0? Beta 0 is dimension of H0. Right? So far what we were doing was we were explicitly trying to see what this H0 is, and trying to use this H0 to figure out what its dimension is, and then accordingly figure out what beta 0 is. In this calculation, I'm showing you a simpler way, right? So one of the theorems that I had stated before was that, and in fact I had proved as well, that if you have a vector space V prime, which is given by V quotient S, then the dimension of V prime is dimension of V minus dimension of S. right? So so accordingly we can see that H0 is Z0 quotient B0, hence dimension of H0 is dimension of Z0 minus dimension of B0, right? So this is what we can use now to compute our zeroth Betti number. So we have computed dimension of Z0, this is 4, and dimension of B0 we have computed it to be 3, and the difference turns out to be 1. Right, so for the simplicial complex that we saw, beta 0 turns out to be 1, right? So this is the simplicial complex, recall, right? So this is the simplicial complex, and the claim is that beta 0 turns out to be 1, right? So again, I haven't explicitly told you what this beta 0 is, right? So I encourage you to think in parallel, what does this 1 mean, right? For these higher order Betti numbers, the number corresponded to the number of like Betti P corresponded to the number of P plus 1 dimensional holes, right? What is this 1 over here, and why is it turning out to be 1? I encourage you to think. Okay, you can definitely look it up on the internet, but knowing the answer is not going to help you learn, right? So I want you to do some trial and error, see what is happening, why is it turning out to be this number, and so on and so forth, right? So as part of this exercise, what I want you to appreciate is that we didn't explicitly write down what H0 is, and we didn't explicitly come up with the basis for H0. Instead, we figured out what Z0 is, what B0 is, and we used their dimensions directly to compute beta 0, which is the zeroth Betti number. So let me pause here for a couple of seconds. If you have any issues with the way we computed this beta 0, please let me know. This may be a good time to ask. Let me know if you have any questions. Please feel free to ask any question that you may have. All right, so I don't see any raised hands. So I think I am a genius professor. I can, whatever I teach, everyone understands. Okay, so that's the only interpretation that I can get. All right. So let us advance. So what we have done is we have computed this Betti 0 in the usual homology case. Now we can look at the reduced homology case, right? So again, I haven't told you what is the difference between usual and reduced, and why do we use reduced. Again, I encourage you to think, what could be the reason that this reduced could make sense. But nevertheless, before we try to see what is the use of this reduced, let's first try to compute it, right? So again, what is the difference in the usual and reduced case is that here C minus 1 changes, right? So here there is daba 1, here there is daba 2. Earlier C minus 1 was set to be the trivial vector space. Now we set it to be the this Z2 vector space, right? So recall that Z2 can be thought of as a vector space over Z2 itself. All right. So this is what we have. Now, so in order to compute this H0 again is Z0 quotiented with B0, right? B0 corresponds to the image of daba 1, right? This is what B0 corresponds to. So notice that we haven't changed C1, we haven't changed C0, and consequently daba 1 doesn't change, and hence this part remains unchanged whether we look at the usual homology setup or the reduced homology setup, right? So B0, whatever we computed, okay, will turn out to be one and the same, right? So as we saw before, B0 is a vector space of dimension 3, and here as well it will turn out to be one and the same, right? So the only thing that will change is daba 0. The reason is that we have now changed C minus 1. So recall what Z0 was, sorry, I shouldn't say daba 0, I should have said Z0. Okay, so earlier Z0 was C0. This was in the usual case. Now let's see what happens in the reduced case, right? So in the reduced case, recall how we define the daba 0 operator. So if you have summation Ci Vi, this is equal to summation Ci. right? So this is how this Daba zero operator's definition is changed, right? So now we have to sort of look at all possible zero chains and ask which of those zero chains would get mapped to 0, because that's what is the kernel of Daba 0. So recall Z0 is the kernel of Daba 0. So we are basically interested in knowing all those zero chains which would get mapped to 0, right? Now since this map takes this summation Ci Vi to summation Ci, and these Ci's are your coefficients, so sum of Ci's will be 0 only if you have a support of either support, I mean an even support, right? So you look at all possible zero chains which has a even support, right? So this is a zero chain with support, what should I say, with support of 2, and this is a zero chain of support 4, right? So in this way you list down all possible what should I say, all possible zero chains with either 2 support or 4 support, right? So this is what it turns out to be, right? So you can see that in the reduced homology case, indeed Z0 has changed. Earlier it was C0. Like for example, it could include elements like zero chains with only support 1, right? It could include elements with support, let's say 3, 1 plus 2 plus 3, and so on and so forth. So you can see that in the reduced homology case, that is no longer the case. In fact, this is having lesser number of elements, right? And again, one can see that in this case, this is a vector space which has 8 elements, and it has a basis made up of 3 elements, which is 1 plus 2, 1 plus 3, and 1 plus 4. And from this one can conclude that dimension of Z0 is 3, right? And in this case, one can see that beta 0, again as we did before, beta 0 is a dimension of Z0 minus dimension of B0, right? And in this case, in the reduced homology case, both of them turn out to be 3, hence the final answer is 0. Is this okay? So again, notice that we didn't explicitly write down what H0 is, what are its elements. We didn't write down the basis of H0, but nevertheless, we directly looked at Z0, we directly looked at B0, and we looked at their dimensions and used those things to compute beta 0 over here. Right. So here is the difference between the beta 0 in the reduced homology case and the beta 0 in the usual homology case. So what we have studied is that in the reduced and the usual homology case, all Betti numbers remain the same except the zeroth Betti number. And in the reduced homology case, the zeroth Betti number is 1 less than the zeroth Betti number in the usual homology case. Okay, so that is what has been our observation, and that continues here as well. In the usual homology case, we sort of saw that beta 0 turned out to be 1. Here it turned out to be 0. Right, so it is 1 less than what we saw in the usual homology case, right? And furthermore, what we now interpret is that, look, beta 0 is dimension of Z0 minus dimension of B0. So this part remains the same in both the usual and remains the same in both the usual and the reduced homology framework, right? So whether we work with usual or reduced homology, this part of the calculation doesn't change. What changes it is this dimension of Z0, which means that in the reduced homology, dimension of Z0 actually reduces by 1. Is this okay? So this is one observation that we make as part of this calculation, and you can see that that fact actually holds in general. Okay, and accordingly, one can see that the Betti 0 in the reduced homology case is 1 less than the Betti number in the usual homology case. Okay, so again, I allow you or encourage you to think, okay, what is this 0th Betti number trying to count in the usual and reduced homology? Okay, so in a lecture or two, I'll give you the answer, but nevertheless, I encourage you to think. All right. Okay, so this sort of completes the homology part of the course, meaning it tells you what homology is, how to compute. If I give you a simplicial complex, if I ask you what its Betti numbers are, you should be able to compute, right? So now we sort of come to the, in some sense, the second part of what I am going to teach. Okay, there will be a separate part which Professor Vijay Natarajan would teach, right? So my part in some sense focuses on this. So I should use this right word here. So it should be computational homology, right? So computational homology, right? So this whole course is computational topology. Okay, my focus was on this computational homology part. So in some sense, so far we have covered the homology part of my topic, right? And now our attention will turn to the computational aspects, right? So now that we understand what homology is and so on and so forth, and you must have already seen that, oh, this is getting too complicated, right? Like you saw in the Betty zero computation itself. Okay, writing down what this B0 is, what this Z0 is, okay, just with 4 vertices turned out to be non-trivial. And you can imagine that if you have millions of vertices or billions of vertices, right, which will be the case in real life. Like for example, let's say you want to analyze the relationships between let's say your friends on your social media, right? So all these things are done by advertisers. Okay, they figure out how these relationships are there and so on and so forth. So that is very, very important, right? So you can definitely see that, for Facebook or Twitter or other such social media, indeed the number of vertices will be in millions, billions, and maybe even more, right? So then doing this computations manually is not going to work out, right? So now we would like to ask, is there a computationally efficient way of computing this homology coefficients, that is the different Betty numbers? Okay, so that is what will be our goal for the this second half of this class. Nevertheless, let me stop here. If you have any questions with what we have done so far, please let me know. uh, After this break of few minutes, we will move on to discussing algorithms for computing Betty numbers. Okay. Do you have any questions? All right, so I don't see any raised hands. Okay, so maybe we can advance. All right, so our goal is, we somehow want to look at computational tools for computing the Betty numbers of a given simplicial complex, right? So if I ask you, let's say I want you to write a algorithm to compute the Betty numbers, right? So how would you have approached this problem? I encourage you to think about this while I give the explanation, right? So notice that in all our computations, CP, ZP, BP, and all these things were vector spaces. That is the first observation that must have struck you. And the second thing is that this DABA P is a vector space homomorphism, or it's a linear map, right? Hence, to find these computational tools, it makes sense to look at linear algebra, right? So linear algebra has taught us a lot of things. And as soon as you see vector spaces and linear maps, right, you should directly think of linear algebra and see if you can make use of any of the tools that we studied in linear algebra to help us come up with a computational way to find these Betty numbers, right? So the first thing you must be able to appreciate is that in linear algebra, or what linear algebra teaches you is that if you have a linear map, you can do whatever the linear map does using a matrix vector multiplication. That's it. If you understand this, you will be able to see that, oh, if I can do with matrix vectors, now I know how to handle matrices and vectors in computers, right? So if I can understand what this this linear map does, then I'll be able to find this corresponding matrices and vectors, and then I'll be able to do all those operations in a computer, right? So for that, we have to recall what it means to say that we have a matrix representing a particular linear operator. Okay, so this is something I had covered in my class of linear algebra that I taught last time, but even if you haven't seen this before, it's not very difficult, right? So what are we now trying to do? So let's say we have been given two vector spaces V and V prime. So I'm going to now give a generic story, and then we will modify this story to cater to our interests, right? So let's say we have been given two vector spaces V and V prime, and let's say there is a linear operator between these two vector spaces. Right, now notice that these vector spaces can be made up of, fancy exotic objects. Like for example, in our case, this CP minus 1 and all these things are made up of these, 1 chains and 0 chains. Right, so if you sort of go outside this class and talk about 1 chains and 0 chains, okay, everybody is only going to stare at you. Right, nobody is going to appreciate, they may ask you what are you talking, what's its use, and so on and so forth. Right, however, if you go outside this class and talk about matrices and vectors, that is something that they will definitely understand and appreciate. Right, so that's what we are trying to do. This v and v prime, let's say it is made up of some exotic objects, and let's say there is a linear operator between v and v prime. Is there a way in which we can translate what happens at the top in the language of matrices and vectors? Right, so for that we had this diagram. So let's say v and v prime are R vector spaces, which means the underlying vector space is defined over the field R. Right, so what it means is that if v and v prime are finite dimensional vector spaces, I can find a basis so that the coordinates of elements in V can be represented in, let's say, some Rn. So this n over here is arbitrary. So let's say V is n dimensional, then I can find a basis such that the coordinates of every vector in V can be represented using n coordinates of real numbers. Right, similarly, let's say V prime is a m dimensional vector space, then one can find a way of finding coordinates which can be represented using m real numbers. Right, so notice that the arrow direction is bidirectional over here, which means that you can take a vector V, find its coordinates, and if I give you the coordinates, you would be able to go back and figure out what that vector was. Right, so that's what the fact that this arrow has is bidirectional means. Similarly, this arrow is bidirectional, which means that this map over here is bijective, which means that you can go from here and you can go back here. However, these maps are not bidirectional because these maps need not be bijections. Okay, so that's the reason this only goes in one direction, and that's the reason this goes only one direction. So what we want to do is we want to come up with a matrix, right? So the matrix over here, so I'm using some mistake in this notation. This should be B prime, right? So this notation, what does this mean? This means the matrix representation of T, right? That's what the square bracket means. And notice that I have a basis here and a basis here. So B is the basis that you choose for V, and B prime is the basis that you choose for V prime, right? So B, this is the basis for V, and B prime is the basis for V prime. So notice that in this matrix representation, I explicitly highlight the basis. The reason is that once you change or modify the choice of your basis, the matrix representation will also change. So it is important to keep in mind that the matrix representation depends on the choice of your basis, right? And what does this diagram tell us? This diagram tells us that it commutes, which means that in whichever way you traverse this diagram, you will end up with the same answer, right? So that's what this matrix should do, right? So let's try to interpret this diagram. So first we will move in the green direction, right? So what does that mean? You start with some vector V in this capital vector space V, right? You apply T, so you will end up with T of V. Now T of V will be an element in V prime. That's why I've written over here. Now if you find the coordinates of T of V with respect to this B prime vector basis, you would end up with its coordinates, right? So this representation over here means that T of V B prime is the coordinate of T of V with respect to the basis B prime, right? So I hope you agree that if you traverse this diagram in this way, you start with V, you end up with T of V, and if you look at its coordinates with respect to the basis B prime, this is what you end up with. Now let's traverse this diagram in this direction. So you start with V. First you find its basis coordinates with respect to the basis B. So this is square bracket V sub B, right? So this is the basis coordinates of V with respect to the basis B. And now you take this vector and this matrix and you multiply it, whatever is the result, these two things must be the same, right? So this diagram commutes means that, okay, you take this matrix and multiply it with this vector over here. Okay, this should equal the coordinates of t of v with respect to b prime. This is what this diagram commutes means, and this is how you are supposed to interpret this diagram, right? So we choose b, we choose b prime, so we know this and we know this, right? Because if you know a linear operator, we know how it acts, right? So this information may be available to us, and what we are now interested in is, can we find a matrix that ensures that this relationship is true for all v? Is this okay? So let me pause here for a second or two. If there are any questions with regards to this diagram, please let me know, because this is the diagram that we will use to build our matrix representation for these boundary operators daba p. And once we have these boundary operators, we will use some simple linear algebra operations, and in order to compute this Betty's like the Betty numbers of different dimensions. So do you have any question with this diagram? Yes, Jacob, please go ahead.
R would be in our case C2, right?
Very good. R would be in our case Z2, but I sort of wrote this diagram with R so that, this is just to make sure that you relate it to what we had studied in, our linear algebra class. Okay, right. So that is correct. But what I want to stress, as Jacob pointed out, is that, there is nothing special about R here, right? This diagram can be, can be drawn for any vector space for any field, right? So let's say there is a vector space that is defined over this field F. We can draw such a diagram, and here instead of R, right, instead of R over here, we would have whatever field you work with, right? So in particular, since we are working with this Z2 field, our diagram would look something like this, right? So if our goal is to compute or find out a matrix representation for this daba p operator, right, what we have to do is, we have to look at this diagram over here. So we have CP, we have CP minus 1. Okay, now so I should make sure that these arrows are bidirectional, right? So you identify a basis for CP. This will give you a coordinate representation in Z2 to the power FP. So notice what this FP over here is. FP is the dimension of CP. So recall, CP is a vector space of dimension little fp, which is the cardinality of capital FP, right? So this is the set of all p dimensional faces. Little fp is the cardinality of this. So this represents the number of p dimensional faces, right? So this is the dimension of this space, right? So the way I wrote it as r to the power n, so that's all I'm writing over here. This is Z2 to the power little fp, because this is the dimension of CP, and here I am writing Z2 to the power FP minus 1, because FP minus 1 is the dimension of CP minus 1, right? And we have a similar story here, that this diagram commutes. So what does it mean? You take a chain C, apply this daba p operator, you end up with this daba p of C, and you look at its coordinates with respect to a basis that you choose for this, right? And here, for simplicity, we will choose the standard basis for both CP and CP minus 1. I'll soon explain what is the standard basis. So, so you look at the coordinates of daba p of C with respect to S prime. So this is what you will end up with. So notice that this will be a vector made up of ones and zeros. Okay, because this is an element of this space, right? So this will be a vector of length fp minus 1 of ones and zeros. And this diagram commutes means that if you traverse this diagram in this direction, you should end up with the same answer. So what does that mean? You take C, find its coordinates with respect to the standard basis that you choose for this space. You end up with this. You multiply this vector with this matrix. Whatever is the answer, these two things should match. Okay, so this is what I mean. So you take any chain C, apply daba p on that, look at its coordinates with respect to this S prime basis. Whatever is this vector, this is the vector that you should get when you look at this matrix representation of daba p. and multiply it with the vector representation of C with respect to this standard basis, right? So we know this, we will choose this S, S prime and so on. So we know everything over here except this matrix. Okay, and this is what remains to be computed, and this is what we will do now, right? So now let me quickly explain what this standard basis over here means. By standard basis, I don't mean anything fancy. It means that I will choose this, the different faces, okay, or the p chain corresponding to these different faces. So recall that a p chain is basically a sum of all possible p faces, right? So look at those p chains which have support 1, right? So support 1 meaning it will only have support over these different p faces. So look at those p chains and put them together, and that will be the standard basis for CP. Similarly, you look at all those p minus 1 chains corresponding to the p minus 1 faces, right? So I have sort of used this tau1 to tau fp minus 1 because I wanted to use a different symbol to label the faces in CP minus 1 as compared to the faces in CP, right? So tau1 to tau fp minus 1, these are the p minus 1 chains corresponding to the fp minus 1 p minus 1 faces in the given simplicial complex. So this is the basis, this is the basis. So we have the basis, we have this Daba P operator, and all that remains to find out is the matrix representation for Daba P. Okay, so let me pause here for a second or two. If there are any questions with regards to the choice of basis or this diagram, please ask. I'd be happy to answer. Do you have any questions? Please don't hesitate. I have repeatedly said if you have any questions, please ask. All right. Okay. So I don't see any raised hand, so maybe we can advance. All right. All right. So now our goal is to find this matrix, right? So in order to find this matrix, I will, basically find the individual columns of this matrix, right? So I want to find the ith column of this matrix. So I hope you agree that if I give you a matrix, okay, so let's say I have a matrix something like this. So let's say its columns are C1 all the way up till Cm, right? And if I want to if I want to figure out what Ci is, right, what I can do is I can multiply this with the vector Ei. So what is this vector Ei? It has zeros everywhere except in the ith position where it is 1, and zeros everywhere. So if I take this matrix and multiply it with this vector, I hope you agree that the answer would be Ci, right? So in order to find the ith column of this matrix, what I'm going to do is I'm going to multiply it with Ei. So now I'm going to ask, what is this product, right? So what is this product? Now what we saw above was the following, that this relationship should be true. Okay, so this relationship must be true for every C, right? So now the question is, how can I do this operation over here? Because if I do this operation, this will give me the ith column of this matrix. So my question is, how do I do this operation? In order to do this operation, I sort of rely on this relationship over here. So the first thing I realize is that what is this Ei, right? So I cannot directly use Ei. I need something like this. So the question is, what is the P chain whose coordinates is Ei? So can one of you volunteer and tell me which is the P chain whose coordinates with respect to this basis that we have chosen is Ei? Can one of you tell me? So the question is, yeah, yes, Ganesh, go ahead.
So it will be 0 sigma 1 plus
very good, very good. So all the way up till 1 sigma I plus blah blah blah. Is this okay? Do you agree? This is what you wanted to say, right?
Yes, sir.
Yes, very good. And we will sort of, in shorthand, we will denote this P chain just as sigma I, right? So this is the P chain whose coordinates with respect to this basis that we have chosen is EI, right? So that is what we are trying to do. So let us just use this relation. So we know that DABA P S prime SS prime times EI. This is DABA P S prime, and I will write it in this fashion. I hope you agree that this equals EI, right? So this relationship I hope you can see. Now I will make use of this relationship that is there above. So this must equal DABA P of sigma I and its coordinates with respect to S prime, right? So what is DABA P of sigma I? So this will be, this will be linear combination of all P minus 1 bases in sigma I. So recall that sigma I is a P phase, but if you apply DABA P, you will end up with all P like a P minus 1 chain, which is basically a linear combination of P minus 1 phases, right? So so this will be the output, and if you look at the coordinates with respect to S prime, you just have to look at which phases have coefficient 1, right? So from this, it should not be difficult to see that the matrix representation of DABA P, right? So I will sort of write it this way. So this should, I'm going to write henceforth the matrix as DABA P only. This is, to unnecessarily not write this square bracket SS prime. So when I write it as a matrix, you should be able to interpret that, when I write DABA P and write a matrix near it, you should be able to interpret that I'm actually going to mean this, right? So what is this? So let's try to understand what will be the size of this DABA P matrix, right? So the size of this DABA P matrix, right? You can figure out that, from this commutative diagram, right? It has to take a vector here and map it to a vector in this space. It has to take a vector here and map it to a vector in this space. So from this, you should be able to figure out that DABA P S prime must be a matrix of size Fp minus 1 cross Fp, right? So it must have Fp minus 1 rows and Fp columns. So this will ensure that if you are given a vector in this space, right? So this is a vector in Fp dimensional space. So notice that the number of columns is Fp. The output would be in this space, and this is ensured by the fact that the number of rows in this matrix is Fp minus 1, right? So you can think of this matrix as having Fp minus 1 rows and Fp columns. So you can put all your Fp minus 1 faces on the rows, and you can put all your Fp P faces, right, on the columns. So you take your P minus 1 faces, put them here. You take your P faces and put them on the column, right? So this is what the matrix you have to interpret in the following way. And now the ijth entry over here, right? The ijth entry will be 1 if tau I, this is a P minus 1 phase, is a boundary of this sigma j, which is a P phase, right? So this is how we are interpreting this. So let me again say what I'm doing over here. The first thing we observed is that this DABA P, right? This is a matrix of dimension Fp minus 1 cross Fp. This is the first thing, right? Then the next thing we observed was that if you give as input any of this sigma I as input, what will be the output? The output will be the coordinate representation in the standard basis of this. Now, what would this vector be? So what I'm doing is I take sigma j, right? And this column over here, right? So this column over here, this is corresponding to DABA P of sigma I and its representation in S prime, right? So what will its representation be? It will be a vector of zeros and ones, where we will have 1 if tau I is a phase of sigma j, right? So let's look at a simple example and that will make things clear for you. So here is a simplicial complex, right? And let's say I ask you what is the matrix corresponding to DABA2, right? So in order to figure out what is the matrix corresponding to DABA2, you have to first, imagine what C2 is and what C1 is, right? C2 is a one-dimensional vector space, right? So why is it a one-dimensional vector space? Because it has these two elements, right? What about C1? C1 is a 5-dimensional vector space, right? So it's a 5-dimensional vector space. And why is it a 5-dimensional vector space? Well, it has 5 edges here. This simplicial complex has 5 edges, right? So you can have these 5 edges. You can think of them as the basis for C1, and accordingly you will see that you will end up with a 5-dimensional vector space, right? So the first thing you observe is that this DABA2, the matrix corresponding to DABA2, ideally I should write this as DABA2 S prime, but I'll sort of write it in this sense and expect you to interpret it as a matrix, when we talk of matrices, and interpret it as an boundary operator when we think of it as an operator. All right. So what is this matrix? It has 5 rows and 1 column, right? And the column, you sort of think of it as the one corresponding to this triangle, and these 5 rows correspond to the edges that are present over here, right? So what you do is, so since this has only one column, what I'm saying is, let's say I want to find the first column of this, so I will multiply it with E1. This is equivalent to DABA2 S prime of the coordinates of 1, 2, 3 with respect to S, and this is equal to DABA2 of 1, 2, 3 in S prime, right? So this is 1, 2 plus 1, 3 plus 2, 3, and we have to find its coordinates with respect to S prime, right? And that is exactly what I have written over here. So you see there is a 1 corresponding to 1, 2. There is a 1 corresponding to 1, 3, and there is a 1 corresponding to 2, 3, and all other coordinates are 0. Is this okay? So let me pause here for a second or two. If you have any questions on how I computed this matrix representation, please let me know. I'd be happy to explain it again. Please let me know if you have any questions. It is surprising that nobody has any questions. I remember during my, when I joined my PhD, I was part of TIFR, and in TIFR the class sizes were very, very small. Okay, it used to have 2 students, 3 students, 4 students, and so on. And I remember when I studied my linear algebra course, there were just 3 of us. Okay, and the professor, whenever he used to come, we used to, ask him like so many questions to him, right? And he used to, really, what should I say, feel overwhelmed and, frightened and scared. Oh, whenever I come to the class, I'll have to answer a bunch of questions. And here we have a class of 30 and nobody has questions, which is very, very strange. I don't know why. Okay, I don't know if I'm not teaching it very well, or if it's the understanding is at such a level that most of these things are not very clear to you. Okay, so that's not very good on my part. So anyways, let's see. Okay, so this is this matrix representation for DABA2, right? And now we can accordingly figure out what is the matrix representation for DABA1, right? So again, first thing we have to do is, what is the size of DABA1, right? So for that we have to realize the 2 vector spaces between which DABA1 is defined. So it is C1 and C0. So since this has 5 edges, C1 has dimension 5, and since there are 4 vertices, C0 has dimension 4. So that's why this DABA1 will be a matrix of 4 cross 5 size, right? And now if I have to find the first column of DABA1, what I do is I take the first edge. So let's say 1, 2, right? So let me sort of repeat this exercise so that it's clear. So I want to find the first column of this DABA1 matrix. So I multiplied with E1. I don't know what E1 is, like how I don't know how to multiply this. So what I do is I write this as 1 to S, right? So notice that if you choose this as the basis for C1, and if you look at the coordinates of 1 2 with respect to this basis, okay, then I hope you agree that you would end up with E1, right? So this is equal to DABA1 of 1 2, and we are trying to find its coordinate representation with respect to this basis S prime. So this is 1 plus 2 with respect to S prime, right? So I hope you can see that this is 1 1 0 0, right? So accordingly you can see that whenever there is a vertex which is part of 1 3 of this edge, you have to put a 1 and 0 elsewhere. Similarly 1 and 4, you can see there is 1 here and 0 everywhere, and so on. See, I don't want you to just memorize that, okay, where to put ones and zeros. Okay, so that would have been maybe good enough in your high school, right? But here I want you to appreciate why we have this rule, right? So this is what I'm trying to motivate over here, why we have this rule. Because tomorrow, if let's say you work in industry and for some reason you cannot work with Z2 coefficients, you have to work with some other field, right? So you cannot use this memory, I mean you cannot memorize this formula and go over there and try to do something. Okay, so that's really not how a scientist should think. The scientist should know the reason, what is the reason behind the why we write this vector in this fashion, right? So if you understand this, if someone has to change the field, you will be able to recreate this matrix accordingly. Is this okay? So that's the reason I'm sort of motivating why this is okay. You can look at the textbook as well, okay, and there they have just given the reason how you have, I mean there they have just given how you have to construct this matrix, but they have not given you the reason. I tried to give you this reason. All right, okay, so in this way you can see that we will have a matrix for DABA2, DABA1 and so on. So one can ask, would we have a matrix for DABA0 as well? Well, if you are in the usual homology, then the DABA0 matrix will have 0 columns, because the C minus 1, sorry, C minus 1 would be trivial, right? And DABA0 in that case, would have 0 columns, right? So it doesn't make sense to write this DABA0 matrix when we are working with the usual homology. Similarly, DABA minus 1, DABA minus 2 and so on, and also this DABA P for higher order, like for higher values of P, okay, there will be no matrices because either the row or the column would be 0, right? Hence it doesn't make sense, right? So now with that I mean that in this example of interest, it suffices to list down only DABA2 and DABA1. That's what I wanted to say, right? So now let's see how we can compute the kth Betti number using these matrices, right? So what is Betti k? So recall that Betti k is the dimension of hk, right? So what is hk? So hk is zk quotient with bk, right? And it's the dimension of this, and this is dimension of zk minus dimension of bk, right? So this is something we know. So I've just copied that over here, that beta k, that is the kth Betti number, is the dimension of zk minus the dimension of bk, right? And what is zk? Well, it is the kernel of DABA of k, right? This is the definition of this zk, and similarly bk is the image of DABA k plus 1, right? So we have now matrix representation for DABA k and DABA k plus 1. So now we can interpret this dimension of kernel of DABA k as the rank of null space of DABA k minus the rank of column space of DABA k plus 1, right? So this is the formula that we will sort of use to sort of write algorithms to compute the Betti number of any dimension, right? So you have a matrix for DABA k matrix representation for DABA k and DABA k plus 1. You have to look at the rank of the column space of this matrix and the rank of the null space of this matrix, right? And subtract these two numbers, you will be able to figure out beta k, right? So maybe this is a good place to stop, because to go ahead I would need some more time, and I think we are at the end of the class. Okay, but nevertheless you should be able to appreciate that using this formula, it should now be possible for you to come up with a way to write a computer algorithm to compute the Betti numbers of any simplicial complex. Okay, so I hope at least this message you can take back home. Okay, and in the next class we will formally discuss how to compute these ranks and rank of this null space and rank of this column space. So let me stop recording over here.